What if one of the most trusted truths of our universe wasn't as solid as we've always believed? For over a century, the speed of light has stood as an unchanging constant, a cosmic speed limit woven into the very fabric of reality itself. We've built satellites, mapped the cosmos, and even defined the nature of time and space around this one number, 299,792 kilometers per second. But what if that number isn't as constant as Einstein imagined? What if light doesn't always travel at the same speed everywhere across distant galaxies, deep within black holes, or even at the quantum level? It's a possibility that doesn't just tweak the edges of physics, it rewrites them. Today, we're setting off on a journey to explore 22 captivating theories that challenge this foundational idea. From the shimmering edges of black holes to the frothy turbulence of spacetime itself, scientists are asking daring new questions about light's behavior. Could it be that the speed of light changes over time or varies across different dimensions? Could ancient light carry secrets about a universe where constants weren't so constant after all? What we're beginning to understand is that this isn't just abstract speculation. It's a quest to solve some of the biggest mysteries in modern cosmology, from the accelerated expansion of the universe to the strange connectedness of quantum particles. This is more than a scientific debate, it's a reimagining of reality as we know it, and you're invited to come along as we dive into the evidence, the theories, and the breathtaking implications of a universe where light doesn't play by the same rules everywhere. We'll travel from philosophical questions first posed centuries ago to experiments happening right now in underground labs and deep space observatories. So get ready to see the cosmos in a whole new light, because by the end of this exploration, nothing may look quite the same. But to truly grasp why this idea feels so revolutionary, we have to step back in time and understand how the speed of light became a fixed rule in the first place. Our story begins not with Einstein, but centuries earlier. Imagine Galileo Galilei in the 1600s, attempting to measure light's speed with lanterns and shutters on distant hilltops. His methods were too crude to capture the truth, but he sparked a crucial question. Does light even have a finite speed, or is it instantaneous? This puzzle captivated scientists for generations. Then, in the 1860s, a Scottish physicist named James Clerk Maxwell unified electricity and magnetism into a single, elegant set of equations. Within these formulas, a constant appeared, a number representing the speed of electromagnetic waves. When calculated, this number matched the known speed of light almost perfectly. Maxwell had not only discovered that light was an electromagnetic wave, he had, for the first time, derived its speed from fundamental properties of the universe itself. This was a monumental shift. Light's velocity was no longer just a measurement to be taken, but a fundamental constant emerging from the deep laws of physics. Yet a profound tension remained. According to Newtonian mechanics, velocities were relative. If you were on a moving train and threw a ball forward, its speed was added to the train's speed. So, if you were moving through space and measured the speed of a light beam, common sense suggested you should get a different result than someone standing still. But Maxwell's equations insisted the speed of light was always the same number, regardless of the source or the observer. This contradiction baffled the greatest minds of the era. It was a young patent clerk, Albert Einstein, who dared to embrace the radical solution. What if the problem wasn't with light, but with our concepts of space and time? In his 1905 theory of special relativity, Einstein proposed that the speed of light in a vacuum is the one absolute, unchanging constant in the entire universe. To preserve this constancy, space itself must contract and time must dilate for moving observers. This wasn't just a mathematical trick, it was a complete overhaul of reality, placing the symbol c on an untouchable pedestal. This paradigm became the unshakable foundation for virtually everything that followed. General relativity, our best theory of gravity, relies on c being constant to describe how matter and energy warp the fabric of spacetime. Our modern technological world depends on it. The global positioning system in your phone is a perfect example. GPS satellites orbit Earth at tremendous speeds, and their onboard clocks tick at a different rate from clocks on the ground due to relativistic effects. If engineers did not calculate these tiny time shifts using Einstein's constant c, the entire system would fail within minutes, accumulating errors of kilometers every day. From the way we map the cosmos to our understanding of the Big Bang, the constancy of light speed is woven into the operational manual of the universe. But even as this idea solidified into dogma, whispers of doubt persisted. Early attempts to measure light speed showed slight variations. Philosophical debates simmered about whether space was an absolute stage or a relational network, which could imply that constants aren't so constant after all. Einstein himself wrestled with these deeper questions throughout his life. By cementing c as a cornerstone, we gained incredible predictive power, but we may have also closed our minds to other possibilities. Recognizing the sheer weight of this historical consensus is what makes the current questioning so electrifying. To challenge c is not to dismiss genius but to honor the scientific spirit of inquiry, the same spirit that drove Galileo, Maxwell, and Einstein to look at the universe and dare to see it differently. So why, after all this time, are scientists suddenly willing to question such a deeply entrenched pillar of physics? It turns out the universe itself has been sending us hints, tiny anomalies and massive cosmological puzzles that our current models, with their fixed speed of light, struggle to explain. This isn't about rejecting Einstein's brilliance. It's about following the data wherever it leads, even if that path forces us to reconsider our most fundamental assumptions. One of the most compelling motivations comes from the vast scales of cosmology, specifically a conundrum known as the horizon problem. When we look out at the cosmic microwave background, the ancient afterglow of the Big Bang, we see a universe that is incredibly uniform. The temperature is the same in every direction to within 1 part in 100,000. This presents a huge puzzle. According to the standard model with a constant speed of light, these distant regions of the early universe could never have been in contact with each other to exchange heat and achieve this equilibrium. It would be like walking into a grand concert hall and finding that every single musician, without any communication, began playing the same note at the exact same moment. The most popular solution has been the theory of cosmic inflation, a period of faster-than-light expansion in the universe's first moments. But what if the solution isn't that space expanded faster than light, but that light itself simply traveled faster back then? A variable speed of light in the early universe could have allowed those distant regions to communicate and homogenize, solving the horizon problem without needing a separate, inflating field. This cosmological headache is a prime driver for physicists like Joe Megiddo to explore models where c was not always constant. Meanwhile, at the opposite end of the scale, the bizarre world of quantum mechanics presents its own direct challenge to light's supreme speed limit. Quantum entanglement, which Einstein famously called spooky action at a distance, shows that two particles can become linked in such a way that measuring the state of one instantly determines the state of the other, no matter how far apart they are. This seems to imply a connection that operates faster than light, a notion that makes physicists deeply uncomfortable because it appears to violate the causal structure set by relativity. While most interpretations argue that no actual information is being transferred faster than light, the phenomenon relentlessly probes the boundary between quantum theory and relativity. It forces us to ask whether the speed of light is truly the ultimate barrier for all physical phenomena, or if there is a deeper layer of reality where such connections are possible, making our constant seem more of a local rule than a universal law. Beyond these grand theoretical puzzles, our ability to even entertain these ideas is powered by a technological revolution in precision measurement. We are no longer in the era of Galileo's lanterns on hilltops. Modern instruments are astonishingly sensitive. Atomic clocks can measure time so precisely that they would lose less than a second over the entire age of the universe. Interferometers like LIGO can detect ripples in spacetime from colliding black holes billions of light-years away, measuring distortions smaller than 1/10,000th the width of a proton. Satellite observatories like the Fermi Gamma Ray Space Telescope can track high-energy photons across the cosmos, hunting for tiny delays that might reveal if light of different energies travels at slightly different speeds. This incredible precision gives us a new lens through which to examine the fundamental constants. We are now capable of testing whether C has remained truly constant over billions of years or across vast galactic distances, turning a philosophical question into an experimental one. Underpinning all of this is the greatest unsolved problem in theoretical physics: the monumental struggle to unify Einstein's theory of general relativity, which governs the very large, with quantum mechanics, which governs the very small. These two pillars of modern physics are famously incompatible, and their conflict often centers on the nature of space and time concepts that are inextricably linked to the speed of light. In the quest for a theory of quantum gravity, whether it be string theory, loop quantum gravity, or something else entirely, many approaches naturally suggest that spacetime might be discrete, foamy, or otherwise fundamentally different at the smallest scales. In such a framework, the idea of a single, immutable speed of light begins to look like a smooth, classical approximation that breaks down when we look closely enough. The constancy of C may be the casualty of a much deeper reconciliation, a necessary compromise to finally weave the fabric of physics into a single, coherent tapestry. These motivations, cosmological, quantum, technological, and theoretical, converge into a powerful case for keeping an open mind. We are not chasing ghosts, we are following a trail of clues left by the universe itself, clues that suggest our cosmic speed limit might just have a variable sign after all. Now we arrive at our first and perhaps most compelling theory: the possibility that the fine structure constant, a mysterious number known as alpha, might not be so constant after all. Think of alpha as one of the universe's most important dials, governing the strength of the electromagnetic force, the force responsible for holding atoms together, for chemistry, for light itself. Its value is approximately 1/137th, and for decades we've assumed it was fixed across all of time and space. But what if that dial has been slowly turning? This idea is so powerful because alpha is mathematically linked to the speed of light. Its defining equation is alpha equals the square of the electron's charge divided by 4 pi, the permittivity of free space, Planck's reduced constant, and finally the speed of light, c. It's a cocktail of fundamental constants. If careful observations were to show that alpha is changing, then at least one of the ingredients in that cocktail must be changing too. For many physicists, the most elegant and likely candidate is the speed of light itself. The man at the forefront of this detective story is astronomer John Webb and his team. Their laboratory is the cosmos itself, and their evidence comes from the ancient light of distant quasars, extremely bright galactic cores powered by supermassive black holes. As this light travels for billions of years across the universe to reach our telescopes, it passes through vast clouds of interstellar gas. These clouds absorb specific wavelengths of light, leaving behind a unique fingerprint in the quasar spectrum called absorption lines. The precise position of these lines is exquisitely sensitive to the value of alpha at the time and place the absorption occurred. By comparing these ancient fingerprints to the ones we see in laboratories on Earth today, Webb's team has reported something astonishing. Their data suggests that in certain directions of the sky, the value of alpha was slightly smaller billions of years ago. In other words, the universe's dial for the electromagnetic force might have been set to a different number in the distant past. If this variation is real, the implications are staggering. It would mean that the very laws of physics are not written in immutable stone, but are more like a language that evolves over cosmic time. A changing alpha could have profound consequences for our understanding of the universe's history. For instance, the process of Big Bang nucleosynthesis, which created the first light elements like hydrogen and helium, is incredibly sensitive to the strengths of the fundamental forces. If alpha was different back then, the recipe for the universe would have been different, potentially altering the amounts of these primordial elements we see today. Furthermore, some theorists have speculated that a slowly evolving speed of light, driven by a changing alpha, could provide an alternative explanation for the universe's accelerated expansion, a phenomenon we currently attribute to the mysterious force of dark energy. Instead of some unknown energy permeating space, the acceleration could be a sign that the rules of the game, specifically the speed at which light and gravity propagate, have been shifting under our feet all along. Of course, a claim this extraordinary requires extraordinary evidence, and the scientific community continues to debate these findings. Other teams have performed similar analyses with conflicting results, and potential systematic errors in the telescopes and instruments are always a concern. The hunt for conclusive proof is driving a new generation of experiments. Scientists are now building ultra-stable optical clocks so precise that they could detect a drift in the fundamental constants over just a few years. New astronomical facilities like the Extremely Large Telescope will peer even deeper into the cosmic past with sharper vision, looking for this subtle signal across the entire sky. The quest to check the universe's most important dials is more active than ever, pushing our technology to its limits in pursuit of an answer that could rewrite our textbooks and reveal a cosmos that is truly alive and dynamic, its most fundamental constants whispering a story of change across billions of years. Now let's pivot to a theory that takes a radically different architectural approach to spacetime itself. Instead of a single, smooth fabric, what if our universe is woven from two distinct layers, each with its own set of rules? This is the fascinating premise of bimetric gravity. In Einstein's general relativity, the geometry of the universe is described by a single mathematical object called a metric tensor. It's essentially the master blueprint that tells us how spacetime is curved by matter and energy, dictating how everything from planets to light rays will move. Bimetric gravity, an idea with roots in the work of physicists like Nathan Rosen and greatly advanced in modern, massive gravity theories, proposes a daring modification. There isn't just one master blueprint, but two. Our familiar spacetime exists alongside a second, shadow spacetime, each with its own independent metric. This dual architecture universe opens up a profound possibility. The speed of light might not be a single, universal number. Each of these two spacetimes could have its own inherent c, its own local speed limit for light. One immediate and startling consequence is that gravitational waves, the ripples in spacetime first detected by LIGO and beams of light might not necessarily travel at the same speed. In standard relativity, they are both waves in the same fabric and must move in lockstep. But in a bimetric world, a gravitational wave could be a ripple primarily in one metric, while light travels through the other, potentially leading to one outpacing the other. Imagine a major cosmic event like the collision of two neutron stars, which emits both a flash of light and a burst of gravitational waves. In our current model, we expect these signals to arrive at Earth at virtually the same time, delayed only by their different journeys through the interstellar medium. But if bimetric gravity is correct, they could arrive hours or even days apart, because they are fundamentally propagating through different fabrics of reality at different maximum speeds. While no such dramatic separation has been observed yet, even tiny differences in their speeds would be a monumental discovery, shattering a key prediction of Einstein's theory. The implications extend far beyond the speed of waves, reaching into one of the biggest mysteries in cosmology, dark matter. For decades, astronomers have observed that galaxies rotate far too quickly to be held together by the gravity of their visible stars and gas alone. The leading explanation is that an invisible, mysterious substance, dark matter, provides the extra gravitational glue, but bimetric gravity offers a compelling alternative. Perhaps there is no invisible matter. Instead, the powerful gravitational fields at the hearts of galaxies and within vast galaxy clusters could be influencing the relationship between the two metrics, effectively changing the local rules of geometry. In these regions of extreme gravity, the effective speed of light could be different, altering how gravity itself behaves on large scales. This modified gravitational force could perfectly mimic the effects we attribute to dark matter, providing the extra pull needed to keep stars from flying out of their galaxies without requiring any new, undetected particles. It's a classic case of Occam's razor. Is the universe filled with a mysterious, invisible substance we cannot directly see? Or are we simply using an incomplete set of blueprints to understand the geometry we can see? This two-metric framework also provides a fresh perspective on the very beginning of the universe. We previously discussed the horizon problem and how a variable speed of light could solve it. Bimetric gravity offers another pathway. In the incredibly dense, hot environment of the Big Bang, the interaction between the two metrics could have been radically different, leading to a temporary period where the effective speed of light was much higher, allowing the universe to smooth itself out. This presents a serious alternative to the theory of cosmic inflation, suggesting that the universe's early uniformity might not have been achieved by a rapid stretching of space, but by a temporary change in the fundamental constants that govern causality within it. By introducing this second dynamical layer, physics gains an incredible amount of flexibility. It challenges the notion that our constants are truly universal, suggesting instead that they might be emergent properties, a kind of average that arises from the interaction of deeper, more fundamental structures. This elegant idea doesn't just tweak relativity, it expands its vocabulary, offering new ways to reconcile the force of gravity with the other forces of nature, and gently guiding our thoughts toward an even more expansive concept, that these dual metrics might be a glimpse of something even bigger, hinting at the existence of dimensions beyond the four we experience. But if the idea of two metrics redefining our universe is mind-bending, prepare to have your concept of reality stretched even further literally. We now venture into a theory that suggests our entire three-dimensional existence might be just a slice, a mere fragment of a much larger, higher-dimensional cosmos. This is the realm of extra dimensions and brane world scenarios most famously explored in string theory. Imagine our universe not as an island in empty space, but as a three-dimensional membrane, or brain, floating within a higher dimensional space called the bulk. In this breathtaking picture, the fundamental constants we hold dear, including the speed of light, might not be fundamental at all. They could be local, emergent properties confined to our brain, while the true, deeper laws of physics play out in the vast, unseen dimensions of the bulk. The light we see and measure could be just a shadow, a projection of something more complex happening in a realm with more spatial dimensions than we can possibly perceive. This isn't just wild speculation, it's a framework with serious mathematical underpinnings like the Randall-Sundrum model. In this particular scenario, our universe is a four-dimensional brain, three of space, one of time embedded in a five-dimensional bulk. One of the most profound implications is that the different fundamental forces might be treated very differently in this higher dimensional arena. Gravity, being the curvature of space-time itself, could be weak in our world because it is the only force that is free to leak out into the bulk, its strength diluting as it spreads across extra dimensions. But what about light? Electromagnetism is thought to be tightly bound to our brain. Its photons are like waves that can only travel along the surface of our membrane universe. However, even light might not be completely immune to the influence of the bulk. In some models, high-energy photons could potentially interact with or even escape into these extra dimensions. If that happens, the effective speed of light that we measure in our four-dimensional world could vary. It might depend on the energy of the photon or the local geometry of the bulk. A high-energy gamma-ray photon, for instance, might behave slightly differently than a low-energy radio wave because it probes this hidden dimensional structure more effectively, potentially leading to tiny, measurable differences in their arrival times across the universe. This extraordinary idea isn't just proposed to satisfy theoretical curiosity. It offers powerful solutions to some of the most nagging problems in physics. Take the hierarchy problem, for example. This is the puzzle of why gravity is so unimaginably weaker than the other fundamental forces. The electromagnetic force is a trillion times stronger than gravity. Why, in the brain world picture, gravity's apparent weakness isn't intrinsic. It's simply because it operates in a larger playing field. Its strength is diluted from our perspective, trapped on our brain. This elegantly explains the vast difference in strength without needing any fine-tuning of numbers. Furthermore, the mysterious force driving the universe's accelerated expansion, dark energy, could find an explanation here. The energy contained in the curvature of the extra dimensions themselves, or the tension of our brain as it floats in the bulk, could manifest as a repulsive gravitational force on a cosmic scale, a perfect candidate for the dark energy we observe. In this view, the fate of the cosmos is dictated by the geometry of dimensions we cannot see. The true revolution of this theory is its radical redefinition of constancy. The speed of light, c, may not be a fundamental constant of the universe but rather an effective, four-dimensional value. It's the speed limit on our local road, but the cosmic highway in the bulk could have a completely different set of rules and speed limits. What we measure in our laboratories is just a shadow, a projection of a deeper, more complex reality. This shifts the goal of physics from discovering immutable laws to understanding how our perceived laws emerge from a higher dimensional foundation. It suggests that the uniformity we assume across the cosmos might be an illusion, a local condition specific to our region of the brain. Elsewhere in the bulk, or on other brains entirely, the laws of physics, including the speed of light, could be completely different, a concept that naturally leads us into the dizzying possibilities of the multiverse. But before we get there, we must shrink our perspective down from these vast extra dimensions to the very smallest scales imaginable, to a seething, turbulent foam where the very concepts of space and time break down entirely. Now let's shrink our perspective down from those vast extra dimensions to the very fabric of spacetime itself, to a realm so small it defies all conventional intuition. If we could peer down to the Planck scale, a distance of about 10 to the negative 35 meters, many physicists believe we wouldn't find a smooth, continuous void, but a seething, turbulent ocean of chaos. This is the concept of quantum foam, a term coined by the legendary physicist John Wheeler. In this breathtaking picture, the vacuum of space isn't empty at all. Instead, it's a bubbling, frothing sea of virtual particles and tiny wormholes, constantly popping in and out of existence due to the inherent uncertainty of quantum mechanics. At this unimaginably small scale, spacetime itself loses its smooth geometry and becomes grainy, fluctuating, and fundamentally fuzzy. It's as if the universe's canvas is woven from a dynamic, living mesh rather than a static, smooth sheet. In such a chaotic, foamy environment, the very idea of a fixed, constant speed of light begins to unravel. Imagine a photon, a particle of light traveling across the cosmos. In Einstein's smooth spacetime, it glides unimpeded at a steady 299,792 kilometers per second. But if spacetime is a quantum foam, that photon's journey is more like a car driving down a desperately bumpy, pothole-ridden road. It wouldn't travel in a perfectly straight line at a perfectly constant speed. Instead, its path would be jostled by the violent fluctuations of the foam. With each step, it would encounter tiny, random hiccups in the fabric of reality, causing its speed to fluctuate unpredictably. In this view, the constant c that we measure in our laboratories isn't a fundamental, unchanging speed limit. It's merely a statistical average, a large-scale, smooth approximation that emerges from trillions upon trillions of these random quantum fluctuations. Over long distances and times, the bumps and wiggles average out to the number we know, but at the most fundamental level, the speed of light is not absolute. It is probabilistic, foamy, and uncertain. This isn't just a philosophical thought experiment. It's a theory that makes a concrete, testable prediction. If the quantum foam is real, its graininess should affect photons of different energies in different ways. A high-energy gamma-ray photon, with its incredibly short wavelength, would be more sensitive to the tiny potholes of the foam than a long-wavelength radio wave. It's like comparing a sports car to a heavy truck on that bumpy road. The sports car, the high-energy photon, would feel every single bump and would be jostled more significantly, potentially slowing it down or speeding it up by a minuscule amount relative to the truck. This means that two photons emitted simultaneously from a violent cosmic event, but with different energies, could actually arrive at Earth at slightly different times. This is precisely what astronomers are trying to detect. Their most powerful tool for this hunt is the light from gamma-ray bursts, the most energetic explosions in the universe since the Big Bang. These events, often occurring billions of light-years away, unleash a torrent of photons across the entire spectrum of energy in a fraction of a second. Telescopes like the Fermi Gamma-Ray Space Telescope are designed to capture this light with exquisite timing precision. By analyzing the arrival times of high-energy and low-energy photons from the same burst, scientists can hunt for those telltale delays that would betray the foamy texture of spacetime. While no definitive, universally accepted signal has been found yet, the mere fact that we can even conceive of such an experiment shows how far we've come. We are no longer just theorizing about the quantum vacuum. We are using the entire universe as a laboratory to probe its structure. The implications of this idea are profound, challenging the very core of Einstein's relativity, which is built upon a smooth, classical spacetime. Quantum foam suggests that this smoothness is an illusion, a convenient approximation that works perfectly well for our everyday world, but breaks down spectacularly at the foundation of reality. It proposes a universe where the stage itself is alive with quantum energy, and the actors like light have to navigate its turbulent waves. This seamlessly connects the world of the very small described by quantum mechanics with the large-scale world of gravity, offering a potential pathway toward the long-sought theory of quantum gravity. It forces us to replace certainty with probability, not just for the position of a particle, but for the very constants that define our universe. And as we contemplate this foamy, uncertain vacuum, we are naturally led to wonder what else might be fluctuating within it, pulling our attention to the mysterious energy that fills even the deepest voids of space. But what if even the vacuum of space, the very stage upon which light travels, is not the pristine, empty void we imagine it to be? Quantum field theory, our most successful framework for describing particles and forces, reveals a stunning truth. What we call a vacuum is not empty at all. Instead, it is a seething, bubbling sea of quantum activity, where virtual particle-antiparticle pairs constantly flicker into and out of existence, borrowing energy from the vacuum itself for fleeting moments before annihilating and returning it. This ceaseless activity has a profound effect on the space around us, a phenomenon known as vacuum polarization. Just as light passing through a medium like water or glass is slowed down because it interacts with the atoms in that material, light traveling through this polarized quantum vacuum could, under the right conditions, have its effective speed altered. The constant creation and annihilation of these virtual particles polarizes the vacuum, effectively turning nothingness into a kind of subtle medium with its own properties. This means that the speed of light, c, might not be an absolute constant for a perfect void, but a value that can be influenced by its environment, becoming context-dependent in ways Einstein never anticipated. One of the most fascinating and mind-bending predictions of this effect is known as the Scharnhorst effect, proposed by physicist Klaus Scharnhorst in the 1990s. He calculated that if you could confine light to travel through the narrow gap between two perfectly parallel, perfectly conducting metal plates placed extremely close together, a setup known as a Casimir cavity, something extraordinary should happen. The presence of the plates restricts the types of virtual photons that can pop into existence in that tiny space. It effectively modifies the quantum foam, suppressing some of the longer wavelength fluctuations that would be present in an unbounded vacuum. According to the math, this subtle alteration of the vacuum structure would reduce the light's interaction with virtual particles, allowing it to propagate just a tiny bit faster in that gap than it would in free space. It's a theoretical prediction that light could, in a sense, exceed its own cosmic speed limit, not by breaking the rules, but because the rules themselves are defined by the vacuum, and we've just changed the vacuum structure. Now, it's crucial to understand that this effect is unimaginably small. The predicted speed increase is so minuscule that it would be utterly impossible to measure with current technology, and it remains a tantalizing theoretical curiosity. But its very existence is a profound revelation. It demonstrates that the vacuum itself is a participant in physics, not just a blank slate, and that by manipulating its properties, we might one day manipulate the very constants we thought were immutable. This concept of a dynamic vacuum doesn't just apply to delicate laboratory experiments. It scales up to the grandest stage of all, the entire cosmos. As our universe expands, the density of matter and energy within it changes dramatically. In the incredibly dense, hot environment just after the Big Bang, the quantum vacuum would have been buzzing with an intensity we can scarcely imagine, flooded with high-energy virtual particles and fields. In such a polarized state, the effective speed of light could have been significantly different from the value we measure today in our cold, sparse universe. Some cosmological models even suggest that a rapidly changing vacuum energy density during these early moments could have driven a temporary but drastic increase in light speed, providing an elegant alternative solution to the horizon problem without needing a period of inflation. The idea is that the universe homogenized not because space expanded faster than light, but because light itself traveled faster when the vacuum was in a different, more energetic state. Furthermore, as the universe continues to expand and dark energy allegedly causes the vacuum energy density to become dominant, could the speed of light be slowly, imperceptibly changing even now? It's a speculative but compelling thought that links the microcosm of quantum fluctuations to the macrocosm of cosmic evolution, suggesting that the history of the universe might be written not in fixed constants, but in the evolving properties of what we mistakenly call empty space. This theory fundamentally shatters the classical notion of a passive, static void. It reveals that empty space is in fact a rich and complex entity, brimming with latent energy and potential. The constancy of the speed of light, therefore, may not be a fundamental law etched into the universe's foundation, but rather a stable equilibrium value that emerges from the average behavior of the quantum vacuum in our current low-energy epoch. It is a constant that depends on the context, on the energy of the environment, and on the very history of the cosmos. This realization doesn't diminish the majesty of physics, it deepens it, showing that even the void is alive with possibility. It sets the stage for an even more radical cosmological idea, that the speed of light wasn't just different in the past due to vacuum effects, but that it was a fundamental, dynamic variable that actively shaped the birth of the universe itself. This brings us to one of the most audacious and sweeping theories on our list, a concept that doesn't just tweak the rules at the edges but rewrites the entire first chapter of the universe's story. It's called variable speed of light cosmology, and its most prominent champion is the brilliant and provocative physicist Joe Megiddo. The central idea is as radical as it is simple. In the fiery first moments after the Big Bang, the speed of light was not a fixed 299,792 kilometers per second. It was astronomically faster, perhaps billions of times faster, allowing it to effectively connect the entire newborn cosmos in an instant. Then, as the universe expanded and cooled, this primordial speed limit rapidly dropped, decaying down to the constant value we know and love today. This isn't a minor adjustment, it's a complete paradigm shift that offers a powerful alternative to the reigning theory of cosmic inflation. To understand why this is such a compelling idea, we need to revisit the horizon problem, one of cosmology's greatest puzzles. When we look at the cosmic microwave background, the oldest light in the universe, we see a sky that is almost perfectly uniform. The temperature is the same in every direction to within 1 part in 100,000. This creates a massive headache for the standard Big Bang model. According to that model, these distant regions of the early universe were never in causal contact with each other. There simply hasn't been enough time since the beginning of the universe for light or any form of information to have traveled between them to even out their temperature. It's like walking into a vast, crowded room and finding that every single person, without having ever spoken to each other, is wearing exactly the same outfit. The most popular solution for the last few decades has been cosmic inflation, a theory proposing that the universe underwent a period of fantastically rapid, exponential expansion in its first fraction of a second, stretching a tiny, homogeneous patch into our entire observable universe. But inflation, while successful, is a complex add-on requiring new speculative physics. Megiddo's variable speed of light cosmology offers a beautifully elegant alternative. The problem isn't that the universe was too small. The problem was that light was too slow. If the speed of light was nearly infinite at the very beginning, then every single point in the nascent cosmos could have been in touch with every other point. There was no horizon. The entire universe had time to chat, to mix, to agree on a uniform temperature, and to become homogenized before the speed of light plummeted to its current value and effectively isolated these regions from one another. In this narrative, the universe didn't need to inflate itself into uniformity. It simply used a different set of physical laws to achieve the same result. A theory this bold must make testable predictions to be taken seriously, and variable speed of light cosmology does exactly that. Its most intriguing signature would be imprinted on the cosmic microwave background itself. While the overall temperature is smooth, there are tiny, specific patterns of fluctuations, anisotropies in this ancient light. The detailed statistical properties of these fluctuations, such as the ratio of their strengths on large scales versus small scales, are a precise fingerprint of the universe's early dynamics. The inflation model predicts a very specific fingerprint that has been remarkably confirmed by satellites like Planck. However, some of the data also shows curious, faint anomalies, large-scale patterns that don't quite fit the simplest inflationary models perfectly. Proponents of variable speed of light theories argue that their model can account for these anomalies naturally. Furthermore, because the fine structure constant alpha is intimately tied to the speed of light, a changing c would inevitably lead to a varying alpha. This creates a direct link to the observations we discussed earlier with astronomer John Webb and the light from distant quasars. If we can firmly establish that the fine structure constant was different in the past, it could be powerful, indirect evidence that the speed of light itself was also different. This creates a compelling cross-check, one set of observations from the very early universe and another from slightly later times, both potentially pointing toward the same revolutionary conclusion. By proposing that a fundamental constant can evolve, this theory does more than just solve a cosmological puzzle. It challenges a foundational pillar of 20th century physics. It suggests that the laws of nature we observe today are not the eternal, unchanging laws that have governed the cosmos since the very first instant. Instead, they may be the frozen, low-energy remnants of a more dynamic and flexible set of rules that operated in the extreme environment of the Big Bang. This idea doesn't discard Einstein's relativity. It generalizes it, creating a framework where the constants within the equations themselves can change over time. It transforms cosmology from a search for initial conditions into a search for the evolving laws of physics. This breathtaking shift in perspective naturally pulls our focus toward the mechanisms that could possibly enforce such a dramatic variation, guiding our curiosity toward the deepest and most sought-after theory in all of physics, a quantum theory of gravity that can describe the universe when it was both incredibly small and unimaginably dense. Now we journey into a theory that reimagines the very fabric of reality, not as a smooth, continuous stage, but as an intricate tapestry woven from tiny, indivisible threads. This is the world of loop quantum gravity, a leading contender in the quest to unify general relativity with quantum mechanics. Its central, radical premise is that space-time itself is not infinitely divisible. At the tiniest possible scale, the Planck length of about 10 to the negative 35 meters, the universe becomes granular or pixelated. Instead of a smooth, flowing river of space and time, reality is more like a dynamic, evolving network of interconnected loops, a spin network, where each tiny loop carries a discrete quantum of area or volume. This isn't just a mathematical curiosity. It's a fundamental rewriting of physics that directly challenges the constancy of light speed. In Einstein's universe of smooth, classical spacetime, a photon is a wave rippling across a calm, endless ocean, always moving at the same relentless pace. But in the granular universe of loop quantum gravity, that photon's journey is profoundly different. It's more like a sound wave traveling through a crystal lattice. The photon doesn't glide unimpeded. It interacts with the discrete, granular structure of spacetime itself. This interaction can lead to a phenomenon physicists call dispersion. Simply put, light of different energies and therefore different wavelengths could travel at slightly different speeds. A high-energy gamma-ray photon, with its incredibly short wavelength, would be far more sensitive to the tiny, lumpy structure of spacetime than a long-wavelength radio wave. It's akin to a mouse trying to run across a cobblestone street versus an elephant. The mouse, with its smaller stride, feels every single bump and crack, potentially slowing it down or altering its path, while the elephant's large steps easily glide over the uneven surface. This means the cosmic speed limit isn't a single, universal number for all light, but could depend on the light's energy. This stunning prediction transforms the search for proof from a theoretical exercise into an observational adventure. Astronomers are actively hunting for this effect by studying the most violent and distant events in the cosmos, gamma-ray bursts. These colossal explosions, often marking the death of massive stars or the collision of neutron stars, fire off a blinding flash of light across a huge spectrum of energies all at once. According to standard physics, all these photons, regardless of their energy, should travel across billions of light years and arrive at Earth at exactly the same time. But if loop quantum gravity is correct, the highest energy photons might be delayed by a tiny, almost imperceptible amount, a few milliseconds after their lower energy siblings. Teams using powerful telescopes like the Fermi Gamma Ray Space Telescope and the MAGIC telescopes meticulously analyze the arrival times of these photons, searching for that telltale energy-dependent delay. While the results are not yet conclusive and the expected delays are minuscule, the very fact that we can design such an experiment shows how these abstract ideas are driving real-world science, using the universe itself as a laboratory to probe the fabric of spacetime. The implications of this discrete structure extend far beyond the speed of light, reaching into the most extreme environments imaginable, black holes. In the Standard Model, the center of a black hole is a singularity, a point of infinite density where the laws of physics completely break down. This is deeply unsatisfying. Loop quantum gravity offers a breathtaking escape from this cosmic dead end. Because spacetime is quantized, there is a smallest possible volume. You cannot crush an infinite amount of matter into an infinitely small point. This means the gravitational collapse of a star doesn't end in a singularity, but rather rebounds in a quantum bounce. This could mean that black holes are not eternal prisons, but rather portals or bridges to other regions of the universe, a concept that sounds like science fiction but emerges naturally from the mathematics of loops. This also solves the infamous black hole information paradox, a long-standing conflict between general relativity and quantum mechanics over whether information that falls into a black hole is lost forever. In a loop quantum gravity framework, information is never truly lost because the singularity never forms. It is preserved and potentially released during the quantum bounce. This elegant solution shows how rethinking the nature of space itself doesn't just change one constant. It overhauls our understanding of the cosmos's most mysterious objects. Ultimately, loop quantum gravity presents a universe where the constancy of the speed of light is not a fundamental law. but an emergent property, a large-scale approximation that works perfectly in our everyday world because we are giant beings oblivious to the tiny, quantum-grained nature of reality. The familiar C is an average that emerges from the collective behavior of trillions of spacetime quanta, much like the smoothness of a material emerges from the chaotic jostling of its atoms. This theory doesn't invalidate Einstein. It provides a deeper quantum foundation from which his smooth spacetime and its constant speed of light can arise. It suggests that the absolute rules we've lived by for a century are actually just a very good, very useful approximation of a far more complex and fascinating underlying truth. This profound shift from absolute to emergent principles naturally guides our curiosity toward a much older idea, one that questions whether any property of the universe can be considered in isolation, inviting us to consider a cosmos where everything, even the speed of light, is defined by its relationship to everything else. What if the speed of light isn't a fixed number etched into the universe's foundation, but something more fluid, a value that emerges from the relationships between everything that exists? This profound shift in perspective brings us to relational mechanics, a framework deeply inspired by the ideas of the 19th century physicist and philosopher Ernst Mach. Mach looked at the universe and asked a deceptively simple question about inertia, that property of matter that resists acceleration. Why does an object in empty space resist being pushed? Newton would have said it's an innate property of the object itself, an absolute quality. But Mach proposed a radically different answer. He suggested that an object's inertia isn't about itself in isolation. It comes from its relationship with all the other matter in the entire universe. The distant stars and galaxies, in essence, provide a cosmic reference frame that defines what it means to accelerate. Einstein was so captivated by this idea, dubbed Mach's principle, that it heavily influenced his development of general relativity, though a purely Machian universe was never fully realized in his equations. Relational mechanics takes this core idea that properties are defined by relationships, not absolutes, and applies it to the fundamental constants of nature, including the speed of light. In this view, C might not be a universal decree. Instead, it could be a cosmic conversation. It's a value that depends on the environment, on the distribution of matter and energy throughout the cosmos. If the universe's mass distribution changes over time, perhaps due to the relentless expansion of space or the gradual clumping of matter into galaxies and clusters, then the very constants that govern physics might shift in response. The speed of light could be a dynamic variable, subtly tuning itself based on the grand, evolving architecture of the universe itself. This turns the entire cosmic narrative on its head. We are not just actors on a static stage with fixed rules. The stage itself and the rules of the play are co-created by the actors in a continuous, interdependent dance. Modern physics has developed sophisticated mathematical frameworks to explore this possibility, most notably in scalar tensor theories. These are extensions of Einstein's general relativity, where, alongside the familiar metric tensor that describes the geometry of spacetime, there exists an additional scalar field, a single number that can have a different value at every point in space and time. This field can represent everything from the strength of gravity to the value of fundamental constants. In some of these models, the speed of light is not a lonely constant, but is coupled to this dynamic scalar field. Imagine C being tied to an invisible cosmic dial, and the position of that dial is determined by the local density of matter, the strength of gravitational fields, or the overall expansion history of the universe. In regions of incredibly high density, like near a black hole or in the very early universe, the dial could turn, changing the local speed of light. This isn't just a philosophical fancy. It's a concrete, testable proposal that makes specific predictions about how light should behave in extreme environments, offering potential alternatives to explain dark matter or dark energy without invoking new, invisible substances. This relational perspective is a profound challenge to centuries of scientific thinking. Since the time of Newton, physics has sought absolute, immutable laws, a set of rules that are the same everywhere and forever. Relational mechanics suggests we've been looking at it the wrong way. The laws we discover might not be the fundamental rules. Instead, they could be emergent properties, a kind of average that arises from the complex web of relationships that make up the cosmos. The speed of light isn't handed down from on high. It emerges from the collective gravitational influence of all the matter in the universe. It's a cosmic consensus, not a divine command. This doesn't make it any less real or powerful, but it does make it context-dependent, opening the door to a universe that is far more interconnected and dynamic than we ever imagined. It prepares us to consider that if the overall structure of the cosmos can influence constants, then perhaps specific, exotic structures within it, cosmic fossils from the universe's violent birth, could create localized pockets where the rules of physics are bent, warping the fabric of reality in their immediate vicinity. Now, let's turn our attention to the possible scars left on the cosmos by its own violent birth structures, so exotic they could twist the fabric of reality itself. These are topological defects, and among the most fascinating are cosmic strings. Imagine the universe in its first moments, a seething, hot plasma undergoing a series of dramatic phase transitions, much like water freezing into ice. As it cooled and the fundamental forces we know today began to separate out, these transitions might not have occurred perfectly uniformly everywhere. In some regions, the fields that permeate all of space could have gotten stuck, unable to settle into their lowest energy state. The result, immense, stable flaws in the very structure of spacetime cosmic strings. Think of them as incredibly thin but unimaginably dense cracks in the universe's foundation, filaments of pure energy thinner than a proton but with the mass of a mountain range packed into every centimeter of their length. They would form a network of cosmic cracks stretching across the entire universe, relics of a time when all of reality was 1 trillion times hotter than the heart of the sun. The presence of such a string would warp the geometry of spacetime around it in a profoundly unique way. According to general relativity, a cosmic string creates a gravitational field that is not like a planet or a star. Its immense mass density makes spacetime around it conical, like a pencil tip poking into a rubber sheet. This creates a bizarre effect. If you were to travel in a perfect circle around a cosmic string, you would find that the total angle you traverse is not 360 degrees but slightly less. It's as if a tiny wedge of space has been removed from the circle. This extreme warping doesn't just bend the path of light through gravitational lensing. It could potentially alter the very rules of the game for light propagating in its immediate vicinity. The local metric, the mathematical description of spacetime, would be fundamentally different near a string. And since the speed of light is dictated by the properties of that local metric, it is conceivable that C itself could be different in these warped zones. A photon traveling through the distorted space near a cosmic string might not experience the same cosmic speed limit as a photon flying through the empty void between galaxies. The fabric of space, in this view, is not a uniform canvas. It is a tapestry that might be frayed, patched, and woven with threads of different tension, creating pockets where the constants of physics are subtly, or not so subtly, altered. This isn't just a wild, theoretical possibility. Cosmic strings could provide elegant solutions to some of astronomy's most persistent mysteries. For instance, their immense gravity could act as seeds for the formation of the large-scale structure of the universe, the vast cosmic web of galaxies and clusters we see today. They could also be a potential candidate for dark matter, or at least a component of it. Their gravitational influence could explain the strange motions of stars within galaxies without needing to invoke vast halos of unknown particles. Furthermore, the dynamics of cosmic strings are incredibly violent. They can oscillate, whip through space, and even intersect and form loops. These cataclysmic events would ripple spacetime itself, generating a unique and potentially detectable background of gravitational waves. If we were to detect a gravitational wave signal that doesn't match the chirp of merging black holes or neutron stars, but instead carries the signature of a snapping cosmic string, it would be revolutionary evidence not just for these exotic objects, but for a universe where the fundamental fabric is imprinted with defects from its creation. The hunt for these cosmic cracks is already underway. Astronomers search for their signatures in multiple ways. One method is to look for their gravitational lensing effects. The peculiar conical geometry around a string would create a very specific type of double image of a distant galaxy, not the stretched arcs typical of a galaxy cluster's lens, but a perfectly identical, mirrored pair of images with no distortion in between. Another method is to scour the cosmic microwave background, the afterglow of the Big Bang, for telltale imprints. A moving cosmic string would create a sharp, linear step-like discontinuity in the temperature of this ancient light. While no definitive discovery has been made, the search continues, driven by the profound implication that finding one would be like finding a fossil from the universe's first moments, a direct window into the extreme physics of creation. It suggests that the uniformity we assume across the cosmos might be an illusion, and that the constants we hold dear might be subject to local variations imposed by the topology of space itself, an idea that seamlessly leads us to consider how our entire theory of gravity might need modification on the largest scales. But what if the problem isn't with the contents of the universe, but with our understanding of the stage itself? This brings us to a radical class of ideas known as modified gravity theories, which propose that Einstein's general relativity, while spectacularly successful, might not be the final word on gravity. Instead of inventing new, invisible substances like dark matter and dark energy to explain the cosmos's behavior, these theories suggest we simply need to rewrite the rules of gravity itself. And in doing so, they inevitably cast doubt on one of relativity's most sacred cows, the absolute constancy of the speed of light. Among the most discussed of these alternatives is MND, which stands for Modified Newtonian Dynamics. First proposed by physicist Mordechai Milgrom in the 1980s, MND was born from a desire to explain a very specific puzzle, the rotation curves of galaxies. When astronomers measure how fast stars orbit the center of a galaxy, they find something perplexing. According to Newton's and Einstein's laws, stars on the outer edges, far from the galaxy's central mass, should be moving much more slowly. But they aren't. They're orbiting just as fast as stars closer in. The standard solution is to propose a huge halo of invisible dark matter surrounding the galaxy, providing the extra gravitational pull to keep those stars from flying away. MND offers a different, elegant solution. It suggests that Newton's law of gravity behaves differently in regions of extremely weak acceleration, specifically the incredibly faint gravitational tugs experienced in the outermost reaches of a galaxy. In these low acceleration regimes, gravity becomes slightly stronger than the standard inverse square law predicts. This tiny modification is enough to explain the rapid rotation of stars without needing any dark matter at all. Now, you might be wondering what this has to do with the speed of light. The connection becomes clear when we move from this simple empirical formula to a full-fledged relativistic theory of mind, a theory that must be compatible with the broader framework of Einstein's relativity, where the speed of light is paramount. Building such a theory is notoriously difficult, but brilliant physicists like Jacob Bekenstein have made significant strides with frameworks like TVS, which stands for Tensor Vector Scalar Gravity. In this sophisticated model, gravity isn't mediated by the spacetime metric alone. It involves additional fields, a vector field and a scalar field. This scalar field is like an invisible fluid that permeates all of space, and its value can change from place to place. Crucially, in these models, the physical speed of light is not a lonely constant. It becomes coupled to this dynamic scalar field. This means that in regions where the scalar field has a certain value, perhaps in the deep gravitational wells of galaxies or in the vast, empty voids between them, the effective speed of light could be different. The cosmic speed limit becomes context-dependent, shaped by the local gravitational environment. In a galaxy where wind effects are active, the altered gravity could be accompanied by a subtly different value for c. This isn't a bug, it's a feature. It's a necessary consequence of creating a consistent theory that modifies gravity while still respecting the core principles of relativity. The implications of this are staggering. It suggests that the pillars of our physics are not independent. You cannot simply change the law of gravity without it echoing through every other constant. If gravity is modified, the speed of light might have to flex and bend along with it. This idea extends beyond explaining galaxy rotations. The accelerating expansion of the universe, which we attribute to the mysterious force of dark energy, could also be reimagined. Perhaps the vacuum energy of empty space is interacting with these new scalar fields, causing a gradual evolution of the fundamental constants over cosmic time. In such a model, the acceleration isn't driven by a new form of energy, but by a slow, cosmic-scale shift in the very rules of physics, including potentially the speed at which light and gravitational waves propagate. This provides a breathtakingly unified vision, one set of modified equations that can explain the motion of stars within galaxies and the expansion of the entire cosmos, all while treating the constants of nature as dynamic participants in the universe's story, not passive spectators. The true power of these theories lies in their testability. They make specific, different predictions from the standard dark matter model. For instance, the detailed motions of stars within dwarf galaxies or the gravitational lensing effects around galaxy clusters can serve as crucial battlegrounds. The ongoing Gaia mission, which is mapping the positions and motions of over 1 billion stars in our galaxy with unprecedented precision, is providing a flood of data that could tip the scales for or against these modified gravity ideas. Furthermore, if the speed of light is indeed tied to a scalar field that varies with gravitational potential, then ultra-precise experiments comparing atomic clocks on Earth to those on satellites in space might one day detect a tiny drift in the measured value of c. By daring to modify our theory of gravity, we are forced to question the immutability of every constant we hold dear, revealing a universe that is far more flexible and interconnected than we ever imagined. This journey to the outer edges of gravitational physics naturally pulls our focus from the vast scales of galaxies down to the spooky, instantaneous connections that defy our classical understanding of space and time altogether. Yet here we are in the quantum realm, faced with a phenomenon that appears to do just that. Quantum entanglement, which Einstein himself famously derided as spooky action at a distance, presents us with one of the most profound and enduring puzzles in all of physics. Imagine you have a pair of particles, perhaps 2 electrons or 2 photons, that are created together or interact in such a way that their properties become deeply linked or entangled. According to the rules of quantum mechanics, these particles do not have definite, individual properties like spin or polarization until the moment they are measured. Instead, they exist in a shared, fuzzy state of potentialities. Now, separate these two particles. Send one to a laboratory on Earth and the other to a detector on a spaceship near Alpha Centauri, 4.37 light-years away. If a scientist on Earth measures their particle and finds its spin is pointing up, quantum mechanics tells us that the particle near Alpha Centauri, at that exact instant, will have its spin pointing down. The measurement here seems to instantaneously determine the state of the particle over there, a connection that apparently operates across 4.37 light-years of space without any time delay whatsoever. This is the essence of non-locality, a connection that defies our classical, relativistic understanding of cause and effect, where no signal can travel faster than light. The immediate and tempting conclusion is that some form of information is rocketing between these particles at a speed vastly exceeding the cosmic limit, a clear violation of Einstein's special relativity. This is the uncomfortable tension at the heart of modern physics, often called the Einstein-Podolsky-Rosen paradox. However, the majority interpretation of quantum mechanics, known as the Copenhagen interpretation, sidesteps this issue in a clever, if philosophically challenging, way. It argues that no actual information is being transmitted faster than light. Before either particle is measured, there is no fact of the matter about their individual states. The act of measurement on one particle doesn't send a signal to the other. It instantly defines the reality of the entire entangled system, no matter how vast its parts have become separated. In this view, the speed of light remains the ultimate speed limit for any meaningful, usable information that could be used for communication. You cannot force the particle on Earth to be up and thus send a Morse code message to Alpha Centauri, because the outcome of your measurement is random. Your colleague there just sees a random sequence of ups and downs with no pattern to decode. The spooky action is real, but it is useless for sending a signal, thus preserving C as the barrier for practical communication. But this orthodox view is not the only one on the table. Other interpretations of quantum mechanics suggest that the conflict with relativity might be more direct, and that our understanding of light's role might need a fundamental revision. For instance, pilot wave theory, a hidden variable interpretation first proposed by Louis de Broglie and later developed by David Bohm, offers a radically different picture. In this model, particles are not just fuzzy probabilities. They are real objects with definite positions at all times, guided by a mysterious pilot wave that pervades all of space. This pilot wave is non-local. It instantly responds to changes anywhere in the universe. In this framework, the entangled particles are connected not by a signal, but through this immediate, holistic pilot wave. Information about the state of the entire system is everywhere at once, embedded in the wave itself. This doesn't necessarily mean that energy or matter is moving faster than light, but it does suggest that the foundational arena of physics, the field that guides particles, operates outside the speed of light constraint. It implies that C governs the motion of things within the universe, but not necessarily the underlying informational field that shapes the universe itself. This creates a layered reality where light's speed, while constant for us, may not be the most fundamental barrier in nature. Another class of theories, known as dynamical collapse models, proposes that the wave function, the mathematical object that describes a quantum system, doesn't just collapse upon measurement, but does so spontaneously and continuously in a process that depends on the size of the system. Some versions of these models, like the Garade-Rimini-Weber theory, introduce a tiny non-locality into the laws of physics. This intrinsic non-locality could, in principle, be exploited to send a signal if the conditions were just right, which would directly challenge the inviolability of light speed. While no evidence for such a violation has been found, the very fact that serious physicists are developing models that incorporate faster-than-light processes at the quantum level shows how entanglement forces us to question the universality of C. It pushes us to ask whether the speed of light is an absolute law of nature or a very strong emergent property that holds for the classical world but can be circumvented in the bizarre quantum realm. This blurring of the line between the quantum and relativistic worlds is the central conflict in the quest for a theory of quantum gravity, and it suggests that the constant C we hold so dear might be more of a macroscopic approximation than a truly fundamental, unbreakable rule. This profound reevaluation of light's supreme authority naturally leads us to an even more controversial and speculative frontier, one that asks whether the act of observation itself, the phenomenon of consciousness, could somehow be intertwined with these deepest laws of physics. Now we arrive at perhaps the most speculative and philosophically charged theory on our list, one that ventures beyond the traditional boundaries of physics and into the enigmatic realm of consciousness itself. This idea suggests that the act of observation, the presence of a conscious mind, might not just measure reality but could actively participate in shaping it, potentially influencing even the most fundamental constants like the speed of light. To understand how we get here, we need to revisit one of the strangest aspects of quantum mechanics, the measurement problem. In the quantum world, particles don't have definite properties until they are measured. An electron, for example, doesn't have a specific position or spin. It exists in a blurry cloud of probabilities, described by a mathematical entity called the wave function. According to the orthodox Copenhagen interpretation, pioneered by Niels Bohr and Werner Heisenberg, it is the act of measurement itself that forces this wave function to collapse from a spread-out set of possibilities into a single, definite outcome. But this raises a deeply puzzling question. What exactly constitutes a measurement? Does it require a conscious observer? This is where the line between physics and philosophy begins to blur. If the collapse of the wave function requires consciousness, then the mind is no longer a passive spectator but an active player in the cosmos. Some thinkers, like the Nobel laureate Eugene Wigner and the mathematician John von Neumann, took this idea seriously. Wigner even proposed a famous thought experiment, now known as Wigner's friend, to illustrate the paradox. Imagine a physicist in a lab performing a quantum experiment. Until he looks at the result, the system is in a superposition of states. But what about a friend outside the lab? For the friend, the entire lab, including the physicist, is part of a larger quantum system. This leads to a chain of observers observing observers, with no clear point where the wave function actually collapses. Wigner argued that only consciousness can ultimately break this chain, placing the conscious mind in a unique position in the architecture of reality. From this starting point, it's a speculative but fascinating leap to ask, if consciousness can collapse a wave function, could it influence other aspects of physics? Could the focused intention of an observer somehow affect the very constants that govern the universe, like the speed of light? The idea is that c might not be an absolute number written into the fabric of spacetime, but a value that is in some way dependent on the perceptual or measurement context. In this view, the constancy of the speed of light isn't a law of nature independent of us. It is a stable agreement reached through a vast cosmic process of observation and consensus. It's a notion that feels more at home in Eastern philosophy or idealist metaphysics than in a physics textbook, suggesting that reality is, in some profound way, a participatory phenomenon. It is crucial to emphasize that this is a highly controversial fringe idea, and the overwhelming majority of physicists dismiss it outright. The primary objection is a practical one. It is utterly untestable with our current scientific methods. How would one design an experiment to prove that a conscious mind can alter the speed of light? The idea seems to retreat from any possibility of falsification, moving from the realm of science into pure metaphysics. Furthermore, there are other, less mystical interpretations of quantum mechanics that avoid the problem entirely. The many worlds interpretation, for instance, proposes that the wave function never collapses. Instead, every possible outcome of a quantum event actually occurs, but in a vast, ever-branching multiverse of parallel realities. In this view, there is no special role for consciousness. Observers simply split into different versions of themselves across different branches. Another approach, known as objective collapse models, proposes that wave functions collapse spontaneously when a system becomes too large or complex, a process that has nothing to do with a conscious mind. These interpretations keep physics firmly in the domain of objective, measurable reality. Yet, despite its lack of mainstream acceptance, the consciousness theory persists because it touches on a deep and ancient human intuition about our place in the universe. It resonates with questions that have been asked for millennia. Is the universe a purely mechanical clockwork, or is mind an integral part of its functioning? The idea sparks intense debate not about data, but about the nature of reality itself, forcing us to confront the limits of the scientific method and the assumptions we make about objectivity. It serves as a powerful reminder that our models of the cosmos, however successful, are ultimately human constructions, and that the act of observation might be more deeply woven into those models than we currently understand. While it almost certainly doesn't mean we can think a light beam faster, it challenges us to consider that the constants we discover may be inseparable from the process of discovery itself, a conceptual bridge that elegantly leads us to our next theory, which posits that the entire universe might be a projection, a cosmic hologram where information is the true fundamental currency. This concept takes us from the abstract world of consciousness to a revolutionary principle that reimagines the very nature of reality, not as a three-dimensional volume, but as a two-dimensional surface encoding all the information within it. This is the holographic principle, a stunning idea born from the study of black holes. In the 1970s, physicist Jacob Bekenstein made a remarkable discovery. He found that a black hole's entropy, which is a measure of its information content, is not proportional to its volume, as you might expect, but to the surface area of its event horizon. This was a profound hint that all the information describing everything that ever fell into the black hole is somehow stored or encoded on its two-dimensional boundary. The holographic principle boldly proposes that this isn't just a quirky property of black holes. It's a fundamental feature of our entire universe. The three-dimensional reality we experience, with all its stars, planets, and people, might be a projection, a hologram, emanating from a two-dimensional shell of information at the very edge of the observable cosmos. If this is true, it completely rewrites the rules for how light, and indeed all of physics, operates. In our standard view, light propagates through a three-dimensional volume, and its speed is a fundamental constant of that empty space. But in a holographic universe, light's journey isn't primary, it's a consequence. The true physics is happening on that distant two-dimensional boundary, where information is processed according to its own set of rules. The light we see and measure in our three-dimensional world is just a projection of that deeper, boundary-level computation. This leads to a breathtaking possibility. the speed of light c might not be a fundamental constant at all. Instead, it could be an emergent property, a consequence of how information is stored, processed, and transmitted on the cosmic horizon. The cosmic speed limit would be set by the information density and the processing power of the universe's underlying code. If the information content of a region of space changes, perhaps the effective speed of light within that region could change as well. This idea becomes particularly powerful in extreme environments. Near a black hole where space is wildly curved and information is maximally compressed onto the event horizon, the local rules for light propagation might be drastically different. In the high-energy chaos immediately following the Big Bang, when the universe was a dense, hot fireball, the information density would have been immense. In such a state, the holographic principle suggests that the effective speed of light could have been much higher, allowing information to be processed and the universe to homogenize far more quickly, offering another elegant solution to the horizon problem without the need for inflation. The speed of light becomes a variable that depends on the universe's computational load. The most concrete mathematical realization of this principle is found in string theory through a concept called the AD/CFT correspondence. This is a powerful duality proposed by physicist Juan Maldacena. It establishes an exact equivalence between a theory of gravity operating in a hypothetical higher dimensional universe anti-de Sitter space and a conformal field theory, a quantum theory without gravity, that lives on its lower dimensional boundary. In this breathtaking mathematical map, a process involving gravity and light in the bulk of the universe is perfectly mirrored by a process involving only quantum information on its boundary. The speed of light in the gravitational universe is directly tied to the speed of information propagation and correlation in the quantum field theory on the boundary. This provides a precise framework for how a constant like c could be an emergent, calculated value rather than a God-given number. It reframes the ultimate laws of physics not in terms of forces and fields, but in terms of information theory and computation. While testing such a profound idea might seem impossible, scientists are devising ingenious experiments. The key is to look for subtle signatures that our reality is indeed a projection. One approach involves using incredibly precise laser interferometers, like the ones used to detect gravitational waves. If spacetime has a fundamental pixelated or holographic nature, it would introduce a tiny, inherent graininess or noise into the vacuum at the smallest possible scales. This noise would leave a faint statistical signature in the laser light traveling through the interferometer's arms. By analyzing this noise with excruciating care, researchers hope to find evidence that space is not perfectly smooth, but is instead built from discrete units of information, just like a hologram is built from pixels. Finding such evidence would not only confirm one of the most radical ideas in theoretical physics, but would also solidify the notion that the speed of light is not a primary constant but a secondary, emergent property, a speed limit set by the universe's underlying processor, a concept that beautifully sets the stage for considering a cosmos where every constant, not just light speed, have a different value in a vast and varied multiverse. But what if our entire universe, with its seemingly perfect and finely tuned constants, is just one inconspicuous island in an infinite archipelago of realities, each with its own unique and arbitrary set of physical laws? This is the breathtaking premise of multiverse theories, a concept that radically recontextualizes the constancy of the speed of light. In this vast cosmic landscape, often called the multiverse, the speed of light isn't a universal decree, it's a local ordinance. Some universes in this grand ensemble might have a c that is far slower, perhaps making chemistry and complex structures impossible. Others might have a speed of light so fast that stars would burn out in an instant or that causality itself would become a blur. Our measured value of 299,792 kilometers per second isn't a special, preordained number. It's simply the winning ticket in a cosmic lottery, the value that happened to be drawn in the particular universe that could support our existence. This idea doesn't just emerge from speculative philosophy. It is a natural, and for some theorists, an unavoidable consequence of our most promising attempts at a fundamental theory of everything, particularly inflationary cosmology and string theory. The leading theory for the universe's initial moments, cosmic inflation, proposes that a tiny patch of space underwent a period of hyper-fast exponential expansion, blowing up to become our entire observable cosmos. But many models of inflation suggest this process is eternal. Once started, it never truly stops, continuously spawning new pocket universes in a never-ending chain reaction. Each of these budding universes could undergo a different kind of phase transition as inflation ends, a process that might randomly set the values of its fundamental constants, including the speed of light. In this scenario, our entire cosmic horizon is just one bubble in a frothing sea of universes, each with its own distinct physics. Furthermore, string theory, with its 10 to the 500 or more possible vacuum states, provides a mathematical framework for this mind-numbing diversity. Each stable configuration of the theory's extra dimensions corresponds to a different universe with different effective laws of physics. The speed of light in each of these universes would be a direct outcome of how those dimensions are curled up and stabilized. This multiverse framework provides a powerful and elegant solution to one of the most profound mysteries in all of science, the fine-tuning problem. The constants of nature, like the strength of gravity, the mass of the electron, and yes, the speed of light, appear to be exquisitely balanced on a razor's edge. If any of them were even slightly different, life as we know it would be impossible. Stars wouldn't form, complex elements wouldn't be forged, and the universe would be a lifeless void. The traditional question has been, why is the universe so perfectly tuned for life? The multiverse answer is a cosmic version of the anthropic principle. If it weren't, we wouldn't be here to ask the question. In an infinite multiverse where every possible set of constants is realized somewhere, it is no surprise that we find ourselves in one of the rare habitable universes. Our constant C isn't special, it's selected. It is the value that allows observers to emerge and marvel at its constancy. A natural extension of this idea is the possibility that even within our own universe, this variation might not be confined to distant, disconnected bubbles. Through mechanisms like quantum tunneling or residual effects from the inflationary epoch, there could be domains or defects within our cosmic volume where the local laws of physics are slightly different. Imagine a region of space, perhaps billions of light-years away, where a phase transition never fully completed, leaving a pocket where the vacuum energy is different. In this domain, the effective values of the electric and magnetic constants could be altered, leading to a local speed of light that is fractionally faster or slower than our own. These would be like cosmic safecracks where the dials for reality were turned to a different setting. While such domains would likely be rare and isolated to avoid conflicting with the remarkable uniformity we observe, their potential existence challenges the notion that our physical laws are universal across every cubic centimeter of space. The most pressing question, of course, is whether any of this is testable. Can we find any evidence for other universes or varying domains within our own? Scientists are exploring several fascinating avenues. One promising method is to search for imprints on the oldest light we can see, the cosmic microwave background. If our universe ever collided with another bubble universe in the distant past, the incredible energy released by such a cosmic fender bender would have left a specific, circular pattern of hot or cold spots in the CMB. Astronomers have actively searched for these signatures, and while no definitive evidence has been found, the search continues with ever more precise data. Another approach is to look for evidence of those domain walls within our universe. If a region with a different value of a fundamental constant exists, its boundary would be a physical interface. Light or other particles passing through this boundary could behave in anomalous ways, or the wall itself might generate specific gravitational effects. The fact that we haven't seen such dramatic evidence yet suggests that if they exist, they are exceedingly rare or far beyond our current observational horizon. Yet, the mere possibility that we could one day find a crack in the facade of our universal laws is a powerful motivator, pushing our observations to the limit and forever expanding our conception of reality. But what if we've been asking the wrong question all along? Instead of wondering if light speed is constant, perhaps we should be asking if time itself is constant. This brings us to a truly foundational idea: variable time and relational clocks. The very definition of the speed of light is a ratio, a distance traveled divided by the time it takes. For over a century, we've treated the time part of that equation as an absolute, unchanging yardstick. But what if that yardstick is made of elastic, stretching and compressing depending on where it is and how it's moving? This isn't just a thought experiment. It's a direct consequence of Einstein's own general relativity, which tells us that time is not a universal metronome ticking at the same rate for everyone. A clock in a strong gravitational field, like near a black hole, will tick far more slowly than an identical clock in the empty void between galaxies. A clock racing away from us at a significant fraction of light speed due to the expansion of the universe will also appear to tick slower from our perspective. This means that the very tool we use to measure the speed of light time itself is fundamentally malleable. This leads to a fascinating and subtle distinction. Is the speed of light actually changing, or are we just measuring it with a warped ruler? In the framework of general relativity, the local speed of light in a vacuum is always constant. If you were to pull out a ruler and a clock right next to a black hole, you would still measure light zipping away from you at 299,792 kilometers per second. However, for an observer far away, watching that light struggle to climb out of the black hole's intense gravity, the story is completely different. They would see the light dramatically redshifted and, crucially, would conclude that it is moving incredibly slowly in the deep gravitational well, as if it were trudging through molasses. From their distant vantage point, using their own clock that is ticking at a different rate, the effective speed of light in that region appears to have changed. This isn't a violation of physics, it's a revelation about the relational nature of measurement. The constancy of c is local, but its appearance from afar is relative to the clock of the observer. This idea powerfully connects back to historical debates that long predate Einstein. The great philosophers and physicists like Gottfried Leibniz argued against Newton's concept of absolute time, proposing instead that time is only meaningful as a measure of change between objects. It is relational. There is no master clock for the universe. Time is defined by relationships. In this view, the question, how fast does light go, is incomplete. The full question must be, how fast does light go, as measured by which clock? If the clock you use to measure time is itself influenced by the cosmic environment, by gravity, by velocity, by the expansion of the universe, then the speed you calculate is inherently tied to that context. This challenges the very notion of a universal constant. It suggests that c is invariant only when measured locally, with a clock in the same state as the light being measured. Across the vast reaches of space, where gravitational potentials and relative velocities vary wildly, the effective speed of light becomes a fluid, relative quantity. The implications of this are profound for our understanding of cosmology. The expansion of the universe isn't just galaxies moving apart through space. It's the very fabric of spacetime itself stretching. This means that the scale of space and the flow of time on cosmic scales are not what they were in the past. If we could somehow send a clock back to the early universe, it would not tick at the same rate as our clocks do today. Consequently, if a physicist in the early universe measured the speed of light with their rapidly ticking clock, and we measure it today with our slower ticking clock in an expanded universe, would we get the same answer? The mathematics of general relativity is designed to ensure we do, but it forces us to accept that the units of our measurement are changing along with the universe. This relational view seamlessly merges with the variable speed of light cosmology we discussed earlier, providing a different philosophical and mathematical language for the same stunning possibility, that the constants we hold dear are not fixed, but are intertwined with the evolving story of the cosmos itself, a story where time is not a background stage but a dynamic actor. A concept forces us to confront the most difficult problem in all of theoretical physics. Now we dive into a theory that strips reality down to its most elemental relationships, proposing that the true fabric of the cosmos isn't space or time, but causality itself. This is the world of causal set theory, a profoundly minimalist approach to quantum gravity. Its core premise is as elegant as it is radical. Space-time is not continuous. It is not a smooth, flowing river. Instead, it is a vast collection of discrete, indivisible events like grains of sand. But these grains aren't just randomly scattered, they are meticulously ordered. Each event is connected to others by a single, fundamental relation, cause and effect. One event either precedes another, follows it, or is causally unrelated. This creates a vast, cosmic web of relationships, a causal set, where the only thing that truly matters is which event can influence which other event. In this sparse and beautiful framework, everything we recognize about the universe, the dimensionality of space, the flow of time, and even the propagation of light, must emerge from this underlying network of causal connections. This leads to a stunning reimagining of the speed of light. In our everyday experience, c feels like a fundamental speed limit, a primary constant handed down from on high. But in causal set theory, it is nothing of the sort. The speed of light is not an input, it is an output. It is a derived property that emerges from the structure of the causal set itself. Think of it like the speed of a rumor spreading through a social network. The rumor doesn't have a preordained speed. How fast it travels depends entirely on the connections between people, who talks to whom and how often. Similarly, in a causal set, light is the fastest possible signal, the ultimate rumor. Its speed is determined by the density and arrangement of the causal links in the network. If the set is dense and tightly connected in a region, causality can be transmitted quickly, potentially leading to a higher effective speed of light. If the set is sparse or has an irregular, foamy structure, the propagation of cause and effect could be slower or more meandering. This means that c isn't constant by decree. Its constancy is a contingent fact about our particular cosmic causal set. If the network's properties change either across space or throughout cosmic history, then the speed of light could vary accordingly. One of the most powerful features of this approach is how it effortlessly banishes some of the most troubling monsters in theoretical physics, singularities. In Einstein's general relativity, The centers of black holes and the moment of the Big Bang are points of infinite density and curvature, places where the laws of physics simply break down and calculations return meaningless infinities. This is a clear sign that the theory is incomplete. Causal set theory provides a graceful escape. Because space-time is fundamentally discrete, you cannot pack an infinite amount of matter or energy into an infinitely small point. There is a smallest possible unit, a fundamental grain of space-time. There is no infinitely small. Therefore, the terrifying singularity at the heart of a black hole is replaced by an extremely dense, yet finite, region of the causal set. The physics there would be extreme, but it would not be nonsensical. The theory naturally avoids its own destruction, offering a complete and finite description of reality from the Big Bang to black holes without any need for magical cut-offs or excuses. Furthermore, this framework is inherently background independent. This is a crucial and philosophically satisfying detail. Most theories of physics, even quantum field theory, assume the existence of a static, pre-existing stage, a background spacetime, upon which the drama of particles and forces plays out. Causal set theory builds the stage from the actors themselves. The causal relations between events define the stage. There is no spacetime without causality. The two are inextricably linked. This means the properties of this emergent stage, including the emergent speed of light, are not fixed. They are dynamic and can evolve as the causal set grows and becomes more complex. The causal set that constituted the universe a billion years after the Big Bang was undoubtedly different from the causal set of today, and so the effective constants that emerged from it, like c, might have been different as well. This provides a natural, elegant mechanism for a variable speed of light that is woven into the very genesis of the cosmos, not merely painted on as an afterthought. This purely causal basis for all of physics inevitably hints at other profound effects. If the speed of light emerges from the network, then it's natural to ask if that emergence might be imperfect or noisy at the smallest scales. Could high-energy photons, which probe the very finest structure of the causal set, experience a slightly different effective speed than low-energy photons? This would create an energy-dependent speed of light, a prediction that aligns with other quantum gravity approaches like loop quantum gravity. A high-energy gamma-ray photon might be more sensitive to the granular, discrete nature of the causal links, potentially interacting with the fundamental graininess in a way that slightly delays it compared to its longer wavelength cousins. This creates a direct bridge to observational astronomy, where scientists are already using distant gamma-ray bursts as natural laboratories to test for exactly these kinds of delays, hunting for the faintest whisper of a discrete, causal foundation to our smooth, continuous reality. What if the speed of light itself depends on the energy of the light being measured? This is not science fiction, but a serious prediction emerging from several quantum gravity models, and it proposes a reality where the cosmic speed limit has different restrictions for different vehicles. Imagine a cosmic highway where a massive truck and a tiny sports car are both governed by the same rule. They cannot exceed a certain speed. Now, imagine that rule is suddenly rewritten so that the weight of the vehicle actually changes the speed limit. A heavy truck might have a lower limit while a lightweight sports car is allowed to go faster. In this analogy, the vehicles are photons of light and their weight is their energy. Some theories suggest that high-energy gamma-ray photons might not travel at the exact same speed as low-energy radio waves. This idea, known as energy-dependent dispersion, directly challenges one of the most sacred principles in all of physics, Lorentz invariance. Lorentz invariance is the mathematical heart of Einstein's special relativity. It's the principle that states the laws of physics, including the speed of light, are the same for all observers, regardless of their relative motion or orientation in space. It's the reason why time dilation and length contraction work so precisely. It ensures that if you measure the speed of light while standing still on Earth, or while hurtling through space at 99% of light speed, you will always get the exact same number. It is the foundation upon which our entire modern understanding of space and time is built. To suggest that the speed of light could vary with energy is to kick that foundation out from under the entire structure. It implies that there is a preferred frame of reference in the universe, after all, a fundamental, underlying grid against which motion could be measured. This isn't just a minor adjustment. It's a paradigm shift that would force us to rewrite the textbooks and open the door to an entirely new understanding of physics at its most fundamental level. So how could we possibly test such a profound and subtle effect? The key is to find the most violent and distant events in the cosmos, ones that unleash a torrent of light across the entire energy spectrum simultaneously. Our most powerful natural laboratory for this is the gamma-ray burst. These are cataclysmic explosions, often the death cries of massive stars or the collisions of ultra-dense neutron stars that can briefly outshine entire galaxies. In a fraction of a second, they release a staggering amount of energy, firing off a blast wave of photons that ranges from low-energy radio waves to incredibly high-energy gamma rays. According to standard physics, all these photons, despite their vastly different energies, are created at the same instant and should travel across billions of light-years of empty space to reach us at exactly the same time. Their journey is a perfect race where everyone is supposed to tie for first place. But if certain quantum gravity models are correct, this race might have a winner and a loser. The incredibly high-energy gamma-ray photons could interact with the hypothetical foamy, granular structure of spacetime itself, what physicists call quantum foam. This proposed graininess of the universe at the tiniest Planck scale could act like a subtle cosmic headwind. A high-energy photon, with its incredibly short wavelength, would be more sensitive to this fine-grained structure than a long-wavelength radio photon. It's the difference between driving a low-slung sports car and a high-clearance truck down a cobblestone road. The sports car will feel every single bump and might be slowed down slightly while the truck glides right over them. In this cosmic scenario, the high-energy gamma rays might arrive at our telescopes a few milliseconds after their lower-energy counterparts. This is where our most advanced technology comes into play. The Fermi Gamma Ray Space Telescope and its primary instrument, the Large Area Telescope, or Fermi LET, is a masterpiece of astronomical engineering specifically designed to catch these fleeting bursts of high-energy light. It doesn't just detect gamma-ray bursts, it timestamps the arrival of individual photons with breathtaking precision, down to microsecond accuracy. For over a decade, teams of scientists have meticulously analyzed the data from hundreds of these distant explosions, searching for that telltale energy-dependent delay. They look for a correlation. Do the highest energy photons consistently show up late to the party? The results have been tantalizing but inconclusive. Some analyses of specific bursts have hinted at a delay, sending ripples of excitement through the theoretical physics community. But other bursts show no delay at all, or even hints of the opposite effect. The statistical evidence remains elusive, like a faint whisper that disappears when you try to listen too closely. The implications of a confirmed detection would be nothing short of revolutionary. It would be our first direct experimental peek into the quantum nature of gravity, a realm where our current theories completely break down. It would suggest that spacetime is not a smooth, continuous fabric, but has a structure, a texture, that can be probed by light. This wouldn't just change our understanding of light speed. It would force a profound revision of relativity itself, leading to a new, more complete theory that seamlessly blends the quantum world with the gravitational one. Furthermore, it would create a direct link to the variation of other constants. If the speed of light can change with energy, then the fine structure constant, which is intimately tied to c, might also exhibit energy-dependent effects, creating a complex web of interrelated variables where we once thought there were fixed rules. The search for this tiny delay is more than just a technical exercise. It is a daring attempt to listen for the echoes of a deeper reality, one where the constants we rely on are not anchors, but flags fluttering in the quantum winds of spacetime. But to truly understand this idea, we first need to revisit a fundamental equation that many of us learned in high school physics. The speed of light in a vacuum isn't just a random number, it's derived from two of the universe's most basic properties. Its value is calculated as 1 over the square root of epsilon 0 times mu 0. Epsilon 0 is the electric constant, also known as the permittivity of free space. It essentially describes how much resistance the vacuum puts up against an electric field. Mu 0 is the magnetic constant, or the permeability of free space, and it defines how a magnetic field propagates through a void. For over a century, we've treated these two values, epsilon 0 and mu 0, as fixed pillars, their product locking the speed of light into an unchangeable value. But what if those pillars themselves aren't as steadfast as we believe? What if the vacuum's willingness to permit electric and magnetic fields can actually shift over time or across space? If either epsilon 0 or mu 0 were to vary, even by a tiny amount, the mathematical foundation for a constant c would crumble instantly. The speed of light would have to change accordingly. This isn't a far-fetched speculation. It's a direct consequence of the very definition we've used all along. It forces us to confront a profound question. Are we measuring a fundamental constant of nature, or are we measuring a property of the vacuum that itself might be dynamic? This concept moves from an intriguing possibility to a serious theoretical framework in models that involve dynamic scalar fields, most notably the dilaton field. In the complex tapestry of string theory, the dilaton is a hypothetical particle that plays a crucial role. It's intimately connected to the strength of all physical interactions. As the universe expands and cools, the value of the dilaton field is thought to evolve, and as it changes, it can effectively alter the coupling constants of nature. Think of it as a master tuning dial for the cosmos. In some scenarios, this evolving dilaton field doesn't just affect the strength of forces, it can also change the electromagnetic properties of the vacuum itself. This means epsilon 0 and mu 0 become time-dependent variables, not fixed numbers. In the hot, dense environment of the early universe, the dilaton field would have had a very different value, leading to a vacuum with different permittivity and permeability, and consequently, a dramatically different speed of light. A photon emitted in the first second after the Big Bang could have been traveling in a universe with a completely different set of electromagnetic rules, potentially covering distances that would be impossible under our current cosmic speed limit. This provides an elegant and mechanistic explanation for how light's speed could have been variable, woven directly into the physics of the universe's evolution. The implications of this are not just philosophical, they could provide tangible solutions to some of cosmology's biggest puzzles. Let's consider primordial nucleosynthesis, the process that forged the first light elements like hydrogen, helium, and lithium in the first few minutes of the universe's life. The outcome of this cosmic cooking session is exquisitely sensitive to the expansion rate of the universe and the reaction rates between particles. Those rates are themselves governed by fundamental constants, including the speed of light. Even a small variation in C during those first critical minutes would have altered the delicate balance, changing the predicted abundances of these elements. Astronomers have carefully measured the primordial amounts of helium and lithium, and there are persistent, slight discrepancies between these observations and the predictions of the Standard Model. A variable speed of light driven by changing electromagnetic constants could elegantly resolve this tension, tweaking the model just enough to match what we see in the oldest parts of the cosmos. Furthermore, this idea ventures into the greatest mystery of modern cosmology, dark energy. We know the universe's expansion is accelerating, but we don't know why. The leading explanation is a cosmological constant, a fixed energy density inherent to the vacuum itself. But what if the vacuum's properties aren't constant? If epsilon 0 and mu 0 are slowly evolving over billions of years due to a lingering dilatant field or a similar mechanism, then the energy density of the vacuum would also be changing. This evolving vacuum energy could perfectly mimic the effects of dark energy, driving the observed acceleration without the need for a mysterious, static cosmological constant. In this view, the accelerated expansion isn't caused by a new, unknown force, but is rather a side effect of the vacuum itself gradually changing its electromagnetic character over cosmic time. The stage of the universe is not static. Its very fabric is aging and transforming, and the speed of light is a key signpost of that deep cosmological evolution. This approach grounds one of physics' most abstract mysteries in the tangible, electromagnetic properties of space, creating a direct and testable link between the quantum world of fields and the large-scale structure of the cosmos. While our journey has taken us across the cosmos and into the fabric of spacetime itself, some of the most startling challenges to light's constancy have emerged from right here on Earth, in the tightly controlled, hyper-precise world of particle physics. This is a realm where scientists collide particles at nearly the speed of light, recreating conditions not seen since the Big Bang, and where a single, unexpected result can send shockwaves through the entire foundation of physics. It was in this high-stakes environment that one of the most famous anomalies of the 21st century erupted. In 2011, the Opera experiment, a collaboration of hundreds of physicists, made an announcement that stunned the world. Their meticulous data, gathered over years, suggested that neutrinos, those elusive, ghostly particles that barely interact with matter, had been clocked traveling from CERN in Switzerland to a detector in Italy faster than a beam of light would have made the same trip. The discrepancy was tiny, just 60 nanoseconds over a 454-mile journey, but its implication was colossal. It suggested a direct violation of Lorentz invariance, the very principle that protects the sanctity of the cosmic speed limit. The announcement was met with a mixture of excitement and deep, profound skepticism. The Opera team itself was incredibly cautious, explicitly asking the global physics community to scrutinize their result and help them find the error. And find it they did. After months of intense investigation, the culprit was identified not in the fabric of space-time, but in the frailty of human engineering. A faulty fiber optic cable connection had introduced a timing delay, and an incorrectly calibrated oscillator had compounded the error. The neutrinos were, in fact, obeying the law all along. The faster-than-light result was retracted. Yet, this episode is far from a mere cautionary tale about experimental error. It is a powerful testament to the scientific method in action, a process designed to be ruthlessly self-correcting. More importantly, it highlights a crucial truth. The most intriguing hints of new physics often arrive dressed as frustrating mistakes. The opera anomaly, though ultimately false, forced physicists to think seriously about what a world with faster-than-light particles would actually look like and how we could ever hope to confirm it. It energized the development of ever more precise tests and reminded everyone that our most cherished assumptions must always be open to questioning. This empirical, evidence-driven side of the debate is where theory meets the unforgiving hardness of data. Particle accelerators like the Large Hadron Collider at CERN are not just discovery machines, they are the ultimate arbiters of reality, capable of subjecting our most abstract ideas to rigorous experimental trial. The hunt for Lorentz violation is a prime example. While no particle has been caught red-handed breaking the light-speed barrier, physicists are designing exquisite experiments to probe for far more subtle effects. They are searching for minuscule differences in how particles of different energies or types behave when smashed together at incredible velocities. For instance, some quantum gravity models predict that the spin of particles could precess or wobble in a specific way if Lorentz symmetry is even slightly broken. Others suggest that the very lifetime of unstable particles might change by an infinitesimal amount depending on their direction of travel through the universe. These are not effects you can see with a stopwatch. They require statistics gathered from billions upon billions of collisions, analyzed by algorithms searching for a pattern that shouldn't be there. The motivation for this painstaking search is immense. Finding even the tiniest, most esoteric violation of Lorentz symmetry would be like discovering a single crack in the foundation of a seemingly impregnable fortress. It would be direct, empirical evidence that the speed of light is not an absolute, universal constant under all conditions. It would suggest that in the extreme energies and unimaginable pressures generated within a particle collision, the smooth, classical spacetime of Einstein's relativity gives way to something else, a quantum foam, a granular structure or extra dimensions, where the old rules no longer apply perfectly. Such a discovery would instantly validate decades of theoretical work on variable speed of light cosmologies and quantum gravity, providing a concrete experimental anchor for ideas that have, until now, lived primarily in the realm of mathematics and cosmology. It would open a direct window into physics at the Planck scale, a realm otherwise completely inaccessible to us, simply by using the incredible power of our particle colliders as the most powerful microscopes ever built. This relentless drive to test the absolute limits of our theories on Earth is beautifully complemented by a parallel search happening across the vastness of space. While particle colliders probe the ultra-small, the universe itself provides us with natural accelerators of unimaginable power, capable of hurling particles across billions of light-years. The anomalies sought in the controlled chaos of a detector at CERN find their cosmic counterparts in the light from distant quasars, the pulses from spinning neutron stars, and the afterglow of the Big Bang itself. This creates a powerful synergy, a two-front war on ignorance, where a hint of Lorentz violation in the lab can guide astronomers on where to look in the sky, and a strange signal from a distant galaxy can motivate a new experiment in an underground collider. The opera incident, for all its eventual embarrassment, served to galvanize this entire field of inquiry, proving that the scientific community is not only willing to entertain heretical ideas, but is actively building the tools to go out and hunt for them, refusing to let our current understanding of light speed become a barrier to deeper exploration. While our particle colliders search for hints of Lorentz violation here on Earth, astronomers are scanning the heavens for something equally profound, a sign that the universe itself might not be the same in every direction. This idea directly challenges one of the most fundamental assumptions in all of cosmology, the cosmological principle, which states that on very large scales, the universe is both homogeneous and isotropic. It looks the same in every direction and from every location. It's the guiding belief that there is no special place or preferred direction in the cosmos. But what if that's not entirely true? What if the universe has a subtle grain to it, like wood, with fundamental constants that are slightly different along one axis compared to another? This is the startling possibility raised by the search for anisotropies, or directional dependencies, in the fundamental constants of nature, a search that, if successful, would imply that the speed of light itself might not be a universal constant, but a value that depends on which way you're looking. The most compelling evidence for this cosmic directional dependency once again involves the fine structure constant, alpha. As we've discussed, alpha is intimately tied to the speed of light, and teams led by astronomers like John Webb have analyzed the light from incredibly distant quasars to see if its value was different in the past. But their work took an even more intriguing turn when they began to map not just if alpha changed over time, but where it might be changing across the sky. Their astonishing analysis suggested that the variation wasn't random. Instead, it seemed to align along a specific axis, a preferred direction in the universe they dubbed the Australian dipole. In one grand sweep across the cosmos, their data indicated that in one direction, alpha was slightly smaller billions of years ago, while in the opposite direction, it appeared to be slightly larger. This wasn't just a change over time, it was a fundamental variation across space, a whisper that the laws of physics themselves might have a north and a south. To verify a claim this monumental, the entire arsenal of modern astronomy has been brought to bear. The Planck Space Telescope, which mapped the cosmic microwave background, the afterglow of the Big Bang with exquisite detail, was scrutinized for any matching asymmetry. Could the same directional preference be imprinted on the very first light of the universe? Other teams using the world's most powerful ground-based telescopes, like the Very Large Telescope in Chile, have performed their own independent surveys of quasar absorption lines, searching for this dipole effect. The results have been a mix of confirmation and contradiction, a classic sign of a science field in its exciting, turbulent infancy. Some studies have found hints that support Webb's original dipole, others have found no evidence at all. The uncertainty isn't a failure. It's the sound of the scientific process grinding forward, with each new analysis refining the methods and tightening the error bars. The debate is fierce precisely because the stakes are so incredibly high. Confirming a cosmic dipole would be like discovering that the universe has a built-in compass, and its needle is pointing toward a physics we do not yet understand. The implications of such a discovery would force a radical rethink of our cosmic models. The standard model of cosmology, known as the lambda cold dark matter model, is built upon the foundation of the cosmological principle. It assumes a uniform universe, and this assumption has been spectacularly successful at explaining a vast array of observations, from the abundance of light elements to the large-scale distribution of galaxies. A confirmed anisotropy in the fundamental constants would punch a hole right through this foundation. It would suggest that the universe is not isotropic on the largest scales, meaning our pocket of the cosmos might not be representative of the whole. This could provide a dramatic new way to explain other, long-standing cosmological puzzles. For instance, the observed accelerated expansion of the universe, which we attribute to the mysterious dark energy, might not be accelerating at the same rate everywhere. If the fine structure constant, and by extension the speed of light, varies with direction, then the very tools we use to measure cosmic expansion could be giving us a skewed, direction-dependent picture. What we see as a uniform dark energy force could instead be a local manifestation of a deeper, anisotropic law of physics. This search for a preferred direction is more than just an academic exercise. It's a direct probe into the possibility that our universe was born in a way that imprinted a fundamental asymmetry from the very beginning. Perhaps the violent processes of inflation, the rapid expansion thought to have occurred in the first fraction of a second, did not unfold perfectly uniformly. A slight directional preference in that initial expansion could have stretched quantum fluctuations in one direction more than another, leaving a permanent mark on the fabric of spacetime that manifests today as a variation in the constants. Alternatively, this anisotropy could be a shadow cast by something entirely outside our universe, an influence from the larger multiverse, tilting the laws of physics in our local bubble in one specific way. The hunt for this cosmic grain is ultimately a search for our own origins, an attempt to read the faint handwriting left on the universe from its moment of creation, a signature that would forever change our place in the cosmos, not by making us special, but by revealing that the cosmos itself has a hidden structure we are only beginning to perceive. Yet for all the meticulous precision of our telescopes and colliders, the human imagination has always raced ahead, dreaming of possibilities that lie just beyond the edge of established science. This brings us to the most speculative territory on our journey, a realm where physics flirts with philosophy, and the line between groundbreaking insight and pure science fiction becomes wonderfully blurred. These are the futuristic models, the fringe ideas that propose mechanisms for a variable speed of light so exotic they currently reside in a world without equations or evidence, sustained solely by the power of creative thought. One such concept revolves around the idea of torsion fields. In some extensions of Einstein's gravity, spacetime isn't just curved by mass and energy. It can also be twisted or put into torsion by the spin of particles. A few speculative theorists have proposed that these twisting fields could, under certain conditions, alter the local properties of the vacuum, effectively changing the permeability and permittivity of free space, and thus the speed of light within that region. The idea suggests that if we could somehow generate or harness these intense torsion fields, we might one day engineer the local value of c, perhaps even creating bubbles of spacetime where light travels faster or slower than its standard speed. It's a notion that captures the spirit of science fiction, reminiscent of warp drives and hyperspace, but it remains entirely theoretical, with no known way to generate such powerful torsional effects or any experimental signature that they exist. Another profoundly speculative idea ventures back into the realm of consciousness, but from a different angle than the quantum observer effect. Some models propose that consciousness itself might not be merely a product of the brain, but a fundamental field or force of nature, akin to gravity or electromagnetism. In this view, often associated with certain interpretations of panpsychism, the entire universe could be permeated by a proto-conscious field. The suggestion, then, is that this field could interact with the physical world, potentially influencing the constants that govern reality. A concentrated act of collective intention or a heightened state of awareness might, according to these highly speculative ideas, subtly warp the local fabric of spacetime, inducing a temporary and minuscule change in the measured speed of light. While this concept resonates with ancient philosophical and spiritual traditions that see mind and matter as deeply intertwined, it currently sits far outside the boundaries of testable science. There is no proposed mechanism for how consciousness could exert such a force, no instrument capable of measuring such a field, and no experiment that could reliably distinguish its effects from random chance. Its power lies not in its predictive ability, but in its captivating narrative, a vision of a participatory universe where mind and cosmos are in a constant, dynamic dialogue. These edge ideas, from torsion engineering to consciousness fields, serve a crucial purpose in the scientific ecosystem. They are the wild, untamed cousins of rigorous theory, and they play the vital role of stretching our conceptual horizons. They remind us that our current understanding of physics, for all its power and precision, is almost certainly incomplete. The history of science is littered with ideas that were once considered heretical nonsense before later being embraced as fundamental truth, from continental drift to the existence of atoms. By entertaining these speculative models, we keep the doors of perception open to revolutions we cannot yet imagine. However, this open-mindedness must be fiercely balanced with a rigorous and unwavering skepticism. The crucial distinction between a valuable speculative idea and mere pseudoscience is a pathway to falsification, a clear statement of what evidence would prove the idea wrong. Without that, an idea remains a philosophical curiosity, a story we tell about the universe, but not a scientific theory we can test and trust. This disciplined skepticism is the engine of scientific progress, ensuring that creativity is always guided by evidence and that our journey toward truth is built on a foundation of reproducible fact, not just captivating narrative. These wild frontiers where creativity meets caution prepare us to examine our final theory, which brings us full circle to the very act of seeing itself, questioning whether the constancy of light is a property of the world or a consequence of how we choose to look at it. And so we arrive at our final, and perhaps most philosophically disorienting, theory, one that questions not just the fabric of space-time, but the very nature of reality and our role in defining it. This idea emerges from one of the weirdest corners of quantum mechanics, a phenomenon known as contextuality. At its heart, contextuality tells us that the properties of a quantum particle are not inherent, fixed values waiting to be discovered. Instead, what you find depends entirely on how you choose to look. A quantum particle doesn't have a definite position and a definite spin at the same time. The property you measure and the value you get is inextricably tied to the context of the entire experimental setup. It's as if you asked a friend how they're feeling, and their answer wasn't about their internal state, but about the specific way you asked the question, the tone of your voice, and the room you were both in. The outcome is a creation of the interaction, not a revelation of a pre-existing fact. Now, apply this dizzying principle to our cosmic speed limit. We measure the speed of light with incredible precision using specific instruments, lasers, mirrors, atomic clocks. But what if the value we get, that 299,792 kilometers per second, isn't an absolute truth etched into the universe's foundation? What if it's a contingent fact, a result that emerges from the specific, contextual dance between our measuring apparatus and the photon itself? In this view, the constancy of C isn't a law of nature. It's a stable, repeatable feature of a specific type of interaction. It's the answer we always get when we ask the question in this particular way. But if we were to devise a radically different way to measure it, a method that probes the photon's journey not with clocks and rulers, but through some other quantum property, might we get a subtly different answer? This isn't to suggest the number would change wildly, but that its status as an immutable constant might be an illusion born from the consistency of our methods. The speed of light, then, becomes less of a universal decree and more of a relational property, a value that is defined in relation to the tools we use to ascertain it. This perspective finds a powerful voice in a modern interpretation of quantum mechanics known as cubism, which stands for quantum Bayesianism. Cubism takes the ideas of contextuality and pushes them to their logical and deeply personal conclusion. In the cubist view, quantum probabilities are not objective frequencies of events out in the world. They are subjective, personal degrees of belief. A quantum state is not a description of a system, but a compendium of an agent's expectations for the outcomes of their future experiments. When a physicist assigns a probability to a photon having a certain polarization, they are not describing the photon. They are encoding their own betting odds based on their prior experience and the specific context of the measurement they are about to make. For a cubist, the outcome of any quantum experiment, including one measuring the speed of light, is a personal experience for the agent who interacts with the world. The incredibly stable value of C is then a testament to the remarkable consistency of our shared human experiences and our standardized ways of questioning nature. We all get the same answer because we've all tacitly agreed to ask the same question in the same way, using tools built from the same classical physics playbook. The constancy is in our shared practice, not necessarily in an independent reality. Of course, this is a highly controversial and minority view within physics. The vast majority of working physicists are pragmatic realists. They use quantum mechanics every day as a tool to predict the behavior of the world, and the fact that it works with stunning accuracy is enough for them. They don't lose sleep over whether the electron was really there before they looked. The primary objection to applying this to constants like C is a practical one. It seems to make science itself impossible. If reality is so deeply subjective and context-dependent, how have we managed to build GPS satellites, lasers, and computers that all work with such breathtaking reliability? The cubist response is that the objectivity of science is not found in a mind-independent reality, but in the intersubjective agreement between all the agents doing the science. We all live in a shared world and have learned through a vast collective conversation how to interact with it to get consistent, predictable results. The speed of light is a cornerstone of that shared conversation, a fixed point in our collective map of reality, even if the ultimate territory remains mysterious and personal. This final theory, while perhaps the most speculative on our list, serves as a profound and fitting bookend to our entire journey. It brings us full circle back to the act of observation itself. We began by challenging the constancy of C across the vast scales of the cosmos, in the early universe and in extra dimensions. We end by challenging its constancy across different contexts of measurement and different perspectives of observers. It suggests that the quest to understand the universe is not a process of simply revealing pre-written truths, but a participatory dance of interaction. The constants we discover may be as much a reflection of our methods and our questions as they are of an external, objective world. It doesn't mean that anything is possible or that reality is whatever we wish it to be. The world pushes back with fierce consistency. But it does mean that the line between the discoverer and the discovered, between the observer and the observed, is far blurrier and more beautiful than we ever imagined. It leaves us not with a definitive answer, but with a humbling and exhilarating question. Are we uncovering the universe's rules, or are we, in some small but fundamental way, collaborating in their creation? We've ventured together through 22 extraordinary possibilities, from the subtle dance of the fine structure constant and the dual realities of bimetric gravity to the mind-bending concepts of holographic universes and cosmic consciousness. Each theory, in its own unique way, invites us to reconsider a fundamental truth we've held for over a century. This isn't about discarding Einstein's monumental legacy. It's about honoring the very spirit of inquiry that drove him to revolutionize physics in the first place. The most profound progress in science has always begun with a simple, courageous act, questioning the unquestionable. What if the cosmic speed limit isn't a fixed signpost but a variable guideline, changing with the energy of a photon, the depth of a gravitational well, or even the evolving story of the universe itself? These ideas push at the boundaries of our understanding, not to create confusion, but to spark a deeper, more nuanced conversation about the nature of reality. This journey reminds us that science is not a static collection of facts but a living, breathing process of discovery. The greatest chapters in our scientific history were once dismissed as heresy, only to become the foundation for entirely new worldviews. The pursuit of knowledge thrives on curiosity, on the willingness to look at the data and dare to imagine a different explanation. Whether any of these specific theories ultimately prove true is almost beside the point. Their real value lies in how they stretch our imaginations and force us to refine our models of the cosmos. They are the necessary catalysts for the next great leap forward, the questions that will drive experiments for decades to come, using tools we haven't even invented yet to probe mysteries we are only beginning to articulate. So what does this all mean for you, right here and right now? It's an invitation to see the universe with a renewed sense of wonder. The next time you see a beam of light, whether from a smartphone screen or a distant star, remember that its journey might be far more mysterious and magnificent than we ever thought. That simple beam connects you to the deepest enigmas of existence, from the quantum foam flickering at the smallest scales to the vast, possibly infinite, expanse of the multiverse. Your perspective on reality itself might feel a little different, a little bigger, and that's the true power of these ideas. They expand our minds. Now, we'd love to hear which theory captured your imagination the most. Was it the cosmic cracks of topological defects, the participatory universe of cubism, or the bold vision of variable light speed in the ancient cosmos? Let us know your thoughts in the comments below. This conversation is just getting started. If you enjoyed this exploration into the fabric of reality, be sure to like this video and subscribe to the channel for more journeys to the edges of space, time, and understanding. Thanks for watching.